When you think of a complex robot, you probably picture something like Centauro, which is an emergency response robot. It's about 5 feet tall, it's made of metal, and it accomplishes the high-level task of emergency response by coordinating simpler tasks, such as walking, picking up debris, breaking down doors, and so on. It's able to interact with and manipulate its physical world. In our research, we're interested in a similar goal, but at a much smaller scale. So rather than being made of metal and manipulating debris and doors, our robots are made of synthetic DNA and manipulate small molecules and nanomaterials. So some tasks that our robots might be suited for are coordinated assembly of a tissue or allergen removal from food. Similar to Centauro, in order to achieve these higher level functionalities, our robots need to be able to develop simpler tasks that they're able to put together. But before we talk more about what these robots are able to do, let's talk about how they're built. So DNA is a material that's as interesting for its chemical properties as for its biological ones. It has very strong and very specific chemical bonds. So what you might remember from grade school biology class, A's and T's bind together and C's and G's bind together. So we can take advantage of this property to design custom DNA sequences that when we mix them together, create specific physical systems. We can also take advantage of thermodynamics to build dynamics into these systems without needing to use an external power source. So now let's talk a little bit about what these robots might be able to do. So what could a nanoscale robot that can interact with its physical world do that an electronic computer can't? So imagine that you have a severe allergy and a plate of food in front of you that contains that allergen. What if you could deploy a robot to get rid of that molecule? So in order to achieve this task, the robot would need to perform several simpler tasks. It would need to be able to navigate the complex environment of the food. It would need to be able to pick up the molecule, and it would need to be able to retrace its steps to get back out of the environment. So before we can develop a robot that does that, we need to make sure that these simpler tools are in our toolbox. So my research focuses on developing one of these skills, which is navigating a complex environment, or maze solving. Similar to how you might design an algorithm for a computer to use to solve mazes, we've designed an algorithm that a robot can use to solve mazes. When the robot moves forward, it modifies the track in order to record its progress. When it moves backward, it removes that modification so that if it hits a dead end, it doesn't record the wrong track. When it reaches the end of the maze, it will have developed a trail that is equivalent to the solution of the maze. In my field of molecular programming, we want our physical world to be as programmable as the world inside your computer. DNA robots are one way we can achieve that. As we build more sophisticated systems, we'll be able to compose them together to manipulate the world in more interesting and useful ways. Stay tuned.
Thank you.